morning everyone and welcome to the NPTEL course Advanced Distribution System Analysis and Operation. Today we will start module 4 of our course, which is Distribution Network Optimal Power Flow Analysis. So, the outline of this module 4, that first we will discuss about the introduction of the OPF analysis, that means why it is needed, how it is performed, this kind of discussion. Then different kind of OPF algorithms we will see, what are their benefits and consequences, mathematical formulation of OPF problems. Two popular OPF algorithms we will see, that is the centralized and distributed algorithms. We will see popular commercial solvers normally used to solve the OPF problems. Then multi-period OPF, that means if you have a time varying quantity, time varying input data, then how to manage them in a OPF analysis. And at last we will see, if you have uncertainty involved in your input parameters, then how can you manage those uncertainty in the OPF problem formulation. So, this is the overall content we will cover in module 4. So, first start with introduction to OPF analysis. So, OPF refers to the process of determining the most efficient operating condition for the power system while satisfying technical and operational constraints. What does it mean? It actually means whenever you operate a network, you cannot operate it in an unregulated manner. That means you do not have any aim, you do not have any constraint, you are just running it freely. That is not possible, because every real time operation or every real time system has certain constraint in it. If you do not follow those constraints, then you will violate the physics of that system, and if you do so, then it will collapse. So, OPF says that you satisfy their technical and operational constraints. We have seen the constraints for our DRs, we have seen the constraints for our loads and other equipment or components associated with the distribution network. So, we have to follow their physics. That is the first thing. Second thing, after following them, you have to achieve something. That means you have to gain something from your operation. You cannot afford to lose money if you are doing a good work. So, that means your operating condition will be such that that will be the most efficient. That means that will be the most generous and most, you can say, economic and reliable operation that is possible for your network. Okay. This is a steady state analysis where we determine the operating point that will satisfy the operating constraints while optimizing the particular goal of the network operator. So, if you own the distribution network, obviously it is your interest that you should fulfill by doing the operation of the network, right. So, that optimizing particular goal, that means this goal will be decided by the interest of the distribution network operator. Got it? First, this OPF concept is proposed in 1962 by Carpentier. He is a power system engineer and he proposed it mainly for the transmission grid. And till then, we are using it for different kinds of networks. That means transmission network, we are using it for the distribution network, even we are using the same thing at the microgrid, small microgrid level as well. So, this OPF problem is a real life problem. That means it is not an hypothetical problem that we are formulating just for the sake of mathematics. It has actually been solved every day and every single 5 minutes or 1 minute time interval in all over the India, all over the world, in all the power networks present in this world. But the problem is that OPF problem involves multiple DRs, multiple loads, a big network. So, actually this is a big problem having multiple variables and constraints. So, formulating that problem is itself is a challenging, and the more challenging thing is to solve that problem. So, how we can do that? That is the main goal of the OPF analysis. So, if we see the power grid operation time frame for service unlocking, that means at which time your power networks does which kind of operation. First, if it is a long term thing, like you are planning your network for 10 to 30 years, then we plan the network. That means we'll plan where to connect each and every buses, what will be the electrical distance between two areas or two nodes. That will decide what will be the strength of the poles, how much will be the strength of the conductor, where you should put the underground cable, where you should put the overhead line, where you will put the capacitor bank. This kind of architecture planning will do for 10 to 30 years, because you have to, your system has to survive for at least 20 to 30 years whenever you will install a distribution or a transmission network. So that is called a long term planning. Another sector comes under long term planning, that is of 5 to 10 years, because the life of these equipments generally we keep in the power networks, their life is approximately 7 to 10 years time. Okay, let us say you are trying to install PV panel, you are trying to install storages, you are trying to install a charging station, electric vehicle charging station. So, this kind of planning we do for 5 to 10 years time limit. Okay. So, this comes under your long term planning segment. Now, here comes short term planning. What we do in short term planning? In short term planning, mostly the bilateral energy market mechanism is done. That means, let us say you are a company and you want to buy power from a generating plant. So, you will sign a MOU with him that you will supply, let us say for 1 year a continuous of let us say 3 gigawatt, let us say. Okay. So, this kind of bilateral trading you have done with some generating plants, and this is vice versa, even generating plants also sign MOU with the big industrial customers. So, these are the bilateral energy market, which is normally done for few months to few days, that must be at least greater than of 10 to 20 days. Okay. When you reduce that time frame from the days to the hours, so at that time we know we perform the economic load dispatch and the unit commitment problem, that when you should turn on your and which thermal power unit will be turned on, what will be the generation from them, that we see. After getting this economic load dispatch or the unit commitment solution, you have to determine whether your network can sustain that generation or not. That we perform in the optimal power flow, that comes from hours to the minute time frame and comes under operation schedule and energy management operation. After that, you have real time operation, where you take the decision of the ancillary services provided to the network, and fault clearing and inverter control, that will be of the lesser than minute or seconds time interval. You know that inverter control is a primary control. So, that is in the limit of microsecond control or millisecond control. Your fault clearing should be within millisecond to few seconds control. So, they comes under real time operation. So, this is the overall time frame or operating a power network, whether it will be a distribution network or a power transmission network, irrespective of that, this is your operation time frame for any power network. So, if we see the Venn diagram, then unit commitment is the lowest level. Then you implement for the OPF analysis, you will get whether your network can sustain that generation or not. Then you will go to the energy market to bid for that much of amount, and if you get that, then you will are good, and depending upon how much you will experience about the load growth or how much DERs you are going to plan for the next 5 to 10 or 20 years, you will do the planning. So, you can see the OPF is the basis of your market clearing and also the planning thing. So, without OPF your network cannot sustain or your network cannot operate properly. So, OPF is the base for ensuring economic, safe, reliable and resilient operation of the network. It will give you whether you are getting benefit as a monetary, or your customers are satisfied or not, whether you can survive any fault condition or not, everything, all the information And under all these situations, what will be your operating scenario, whether you can get over from it or not? This all the informations you will get by solving the optimal power flow problem. So, what are the features of an OPF problem? First, OPF focuses on optimizing one or more objective. You can have either one objective to run your network, or you can have multiple objectives to run your network. So, OPF problem can be of single objective type or multi-objective type. We have seen that the model of DERs, especially the model of the network, is a non-linear model. So, OPF is generally formulated as a non-linear programming due to the non-linear nature of some constraints and objective function. We have seen that. We have modeled all the network facilities in our module 2, and we have seen that most of the real time facilities present in the network and the network itself possess a nonlinear and non-convex modeling. The Kirchhoff's voltage and the current law introduces nonlinearity as it relates power flow to bus voltage and phase angles. What we have seen that piece Ij square plus Qij square equals to VL Vi Lij. We have seen this equation, right? So, this equation itself is a nonlinear equation. So, this equation inherently will come when you will solve the OPF. So, your OPF problem due to this kind of constraints, your OPF problem is a nonlinear programming. Because of the nonlinear equality constraint like this, the feasible solution space of OPF is non-convex. Okay. And if you have a non-convex solution space, then finding the optimal solution is a challenging thing. And it is a high probability that you will stuck to a local solution, not to the global solution. There is a very high probability of it, and most of the time it happens. So, that is why we did the convexification. Then OPF models can scale from small microgrids to the large interconnected networks. That I already told. You can do it for a small network with 2-3 buses, you can solve it for the network with 20,000 buses. Then it takes care of the system constraints so that secure and reliable operation is obtained, and multiple solution methods like classical heuristic optimization we follow to solve the OPF depending upon how you are formulating your problem. If your problem is very complex in nature, then you will go with heuristic technique. If it is a direct solution is possible or you have done proper convexification or linearization, then classical optimization technique is good. Okay. So, what is the structure of an OPF problem? If we see, first you have few components. One is the objective function you will have decision variables, you have parameters, you have equality constraints, and you have inequality constraints. Only 5 things you must have in your OPF problem formulation, and that is there. If you formulate an OPF problem properly, you will surely have these 5 things. So, the problem look like this, that will minimize the objective function, that means minimization of your goal. Let us say this is your fx, this x is your decision variables. This is your decision variable. Okay. So, this x you will try to determine, this is your actually you want from your OPF solution. Then this gx equals to c, this is your equality constraint, and bx less than equals to b, this is your inequality constraint. When you will run this optimization, you need some certain parameters that will control your OPF problem or your network. Let us say we have seen that power balance, right? That means the total power generation plus total power load equals to summation how much power is coming to that bus, right? We have seen this power balance equation. So, here you want how much generation or how much power you are getting from your sources, let us say dispatchable sources, and how much power flow you are giving to your next buses, right. So, these things are your decision variables. So, what is your parameter? Your parameter is that load, because you have to know how much load you have to cater. Again, if you have a DER here, so how much generation you are getting from your solar or the wind turbines, that is your parameter. So the objective function is a mathematical expression that guides the optimization algorithm to find the best operating point of the power system while respecting system limits. Okay? That means that will guide you that what you want to achieve. Let us say you want to achieve a minimum cost function, minimum cost condition. So your objective function will structure your OPF or give the solution a direction that ultimately whatever global optimal solution you will get, that will be the lowest cost possible, that will incur the lowest cost possible. Okay? Then the second thing is the decision variable. The decision variables are the control parameters that can be adjusted or optimized to achieve the objective function. That means to minimize that cost, how much generation you have to set or how much allowable power flow you can allow to flow to the through the line. So those are your decision variables. Then parameters. Input parameters are the known and fixed values that define the system configuration and operating environment. These parameters are not optimized but essential for the optimization problem. Okay? That means those are input values. Those will give you that with under this condition you have to get the optimal solution. Then equality constraint represent the physical laws of the power system, that is your power balance, that is your voltage equation. Those are the physics of the system. You cannot violate those physics. If you violate that and get your solution, then that solution you cannot implement on the real life network. Then you have inequality constraints denote the permissible range of the decision variables so that system operates safely. That means that will give an upper or a lower limit for a certain condition or a certain operation. So with this, let us see what are the types of OPF problems you have. You can define your OPF problems or segregate your OPF problems depending upon objective function, network condition, power flow which you are taking like AC or DC, and how you are structuring your problem. So depending upon objective function, your OPF problem can be of two types, single objective or multi objective. That means your objective function can be only one or you have more than one objectives. Okay, got it? Network, you can formulate your OPF for transmission network, that is we call TOPF, or distribution network, that we call DOPF. You can adopt AC power flow or you can adopt DC power flow. Your problem structure can be deterministic, it can be stochastic, it can be robust, risk constrained or dynamic. We will come to this term what they signify. Deterministic means you are not considering any uncertain parameter, stochastic means you are considering uncertain parameters, robust means you are considering the worst case possible from that uncertainty, risk constraint means you are considering the risk associated with that uncertainty, and dynamic you are considering the time varying quantity for a particular input parameter. So depending upon this or combination of this will give you an overall OPF structure. So what is a single objective OPF? Your single objective OPF says that you will minimize or maximize only one objective. That means you have only one objective function f1x that you have to minimize and or maximize to get the decision variable x. So either you will minimize the energy cost or you will minimize the loss or emission. So multi-objective optimization OPF problem that says that you will try to optimize two or more conflicting objective functions simultaneously. They must be conflicting in nature. Let us say take an example that you are trying to minimize the cost. Okay. So there is one option that you can minimize the cost by doing the load shedding. That is an option. But let us say you took that apart from minimization of the cost, you took minimization of the load shedding as well. Because that load shedding means you will reducing the reliability of your system. Your customer will become dissatisfied with your performance. So you will try to minimize that load shedding. So, you want a trade off between load shedding and the cost minimization. But if you see, if you reduce cost, you have to do more load shedding. So, your this objective function value will increase. If you reduce the load shedding, then you have to give more power to the customers. So, your cost will increase. So, these two objective functions are conflicting in nature. So, if any DNO takes these two into consideration simultaneously, then he has to formulate his problem as a multi-objective problem. What are the characteristics of multi-objective problem? Improving one may worsen the another. What I just told. One objective function, if you make it better, the other one will become worse. No single optimal solution is possible. Instead, a set of Pareto optimal solution exists. That means you will not get a single solution that will give you that it is best for all the objective function. That is not possible. You will get a trade-off kind of solution that will give a Pareto optimal that is somehow optimal for all the objective functions. Then a trade-off between multiple solutions will do. So, how we will tackle multi-objective problem? Here are few terms we have to know, that is, first one is called dominance vector. A vector fx1 dominates another vector fx2, that is, it will be lesser than fx1 is lesser than fx2 if you are dealing with a minimization objective, and we conclude that x1 solution dominates x2 if and only if your fi x1 is less than equals to fi x2 for at least one objective. So, you have multiple objective, at least for one objective your one solution is lesser than the objective function value for that solution is lesser than for the objective function value of any other solution. Okay. And for other objective function, it is not the worst solution. It is somehow bad, but it will not be the worst solution. So, then this solution x1 will called as dominance vector. Then Pareto optimality. A feasible solution x cap is called efficient or Pareto optimal to a multi-objective optimization if there is no other solution x. That means you got your solution x cap. So, other than that you have no other solution that will give you an objective function value which is lesser than the objective function value if you implement fx cap. There is no other solution. That means your fx cap will be the most optimal solution for all the objective. If x cap is efficient, then fx cap is called as non-dominated point. The set of all efficient solutions, x cap is denoted by xc and called as the efficient set. The set of all non-dominated points, that means fx cap, is called a non-dominated set. So, we will try to determine from the multi-objective problem this x cap solution. The strict Pareto optimality says the solution x cap is strictly Pareto optimal if for the multi-objective optimization problem there is no other solution other than x cap, that for all the objective functions your x cap will give the minimum value. That means this condition is satisfied, is not satisfied, that there is no other solution x which will give you the lesser value for the fx k. That means for all the objective your fk x cap is always less than of fk x. If you get a solution like this, then you can say your solution is strictly Pareto optimal. So, how to get this Pareto optimal solution? First, you can do the weighted average method, or you can follow epsilon constraint method, or you can use Pareto optimality approach or evolutionary algorithm. So, what is weighted average method? In case of weighted average method, other than dealing with this different objective function separately, what we do? We assign a weight to each and every one and sum all of them. So, your multi-objective problem is now converted to a single objective problem, which will minimize the summation of the all the objective functions multiplied with their corresponding weights. So, summation of all these weights must be equal to 1 and all the weights must be greater than equal to 0. So, weights means you are giving some priority to few objective function. Let us say you are giving some priority of 0.9 to one objective and let us say 0.1 to another objective. That means your solution will be more biased to that objective function which has given more priority. So, what are the advantage? First is that it is easy to implement. Second, it converts the multi-objective problem to the single objective problem. That means you need not to deal with multiple objective functions to in a iteration basis. You can take them together and just solve your problem. And you can prioritize by setting higher weights. That means you can prioritize the list of your objective function from the list of your objective function that which are more, you can say, in line with the interest of yours. Okay. But the limitation is that first you have to select the proper weight, because if you put the weights erroneously, then your solution will become less accurate, or sometimes it can be a completely erroneous result. It only sees the convex regions of the Pareto front and miss the non-convex solution possible. That means it will only see that whether the solution points are lies within the convex set only or not. If you have any solution which is outside that convex set, that solution it will cannot consider. So, that is the limitation. The next method, that is called epsilon constraint method. There what we do? We select one primary objective to minimize or maximize and treats the other objective constraint with upper or lower bounds. That means we will take from multiple objective functions. Let us say we have multiple objective functions, we will take only one objective. That means we will try to minimize only f1x and we will think that f2x value must be lesser than equals to some upper limit value, some upper limit, and we will solve this problem. And we will solve this problem in multiple runs. That means at the first iteration we solve this problem, that will be your iteration 1. For the second iteration we will do the opposite, that minimization of the f2x while considering f1x is less than equals to some upper value, and we will solve that in the iteration 2. And we will continue with all the objective functions, and ultimately the solution will be determined which will give the lesser value, lowest value or the least value or the most optimal value, that we will consider as the Pareto solution. What are the advantage? Focus on one objective while bounding others. That means you have to focus only one and set the others as the upper limit. Can capture non-convex regions of the Pareto front, flexibility to explore different trade-offs by adjusting the epsilon values. That means you can set the epsilon values and you can see how your solutions are varying. Limitation requires careful tuning of the epsilon values. That means let us say you are trying to say that your cost is lesser than of certain amount, but let us say that is not even the minimum value. You have chosen some value which is minimum of your lowest limit, or you can say lower of your lowest limit. So, then you will never get a good solution, never get solution, your solution will never converge. So, this choice of this epsilon value is very critical. Then multiple runs needed to generate the full Pareto front. That means if you have let us say 10 or 20 objective functions, then you have to solve your OPF problem 20 times. Now, you can imagine that for a huge or a bulk system of let us say 10,000 bus system, you are solving your OPF problem 10 times or 20 times. So, that much computation complexity you have to handle, and this become more complex for high dimensional objective spaces, what just I have told. Other than that, you have Pareto optimality approach, which says identify the set of non-dominated solutions forming the Pareto front. No single solution is better in all objectives. That means you will get the solution from the Pareto front search space, but that solution will not be good or the best for all of them. Efficient when all objectives are equally important, when you have weights of 1, so let us say everyone is equal for you. Then we can use evolutionary algorithm, where what we do, generate a huge number of population and search for Pareto optimal solution by modifying the population at each iteration and finding the best solution. This is the evolutionary algorithm we use. We generate a population, we test the feasibility, we test the objective function value, and then modify that population to get the best optimal solution. Two best examples of this evolutionary algorithm is multi-objective particle sum optimization and non-dominated sorting genetic algorithm 2. So, this is the overview of the transmission network OPF. If you are using AC OPF, you will minimize the energy cost or energy generation cost, and then you have this BIM model what we discussed in module 2. This is your branch injection, bus injection models. You have generation limits, reactive and reactive power limits for your generators, your voltage limits and your angle limits. If you go for the DC OPF, same objective function will be there, but your reactive power balance constraint is neglected because in DC we do not take reactive power. Even the loss in the active power is neglected, and this will become your Pg minus PL equals to summation of theta I minus theta j by xij. We will take this DC power flow equations. This is your DC power flow equation. You have generation limits and as well as angle limits. You need not to deal with the voltage magnitude also. So, if you solve the DC OPF, you will get exactly how much load, you will get the generation of that much. You are neglecting the losses. But if you solve the AC OPF, then obviously the total demand, that is load plus loss, that will be greater than, or your generation will be greater than the total, not the loss. Your generation will be total greater than your load demand, and that extra generation will supply the loss. And you can solve it with the traditional gradient, Newton and interior point method. Now, why we will focus on distribution network? First thing is that the changing nature and requirements of the grid, decarbonized and distributed future. We have multiple sources we are connecting with the distribution network, EVs we have solar panels and all these things. So, we can see that very large penetration of distributed energy resources, roughly 250 million solar PV installation we have in India, and rooftop solar penetration of almost 36.1 million. So, you can see how much huge amount of DERs we are integrating with our distribution grid. With new load type, we have 1.6 million of electric vehicles we have added in last year, fiscal year 2024. We have buildings, we have aggregators, microgrids and more active nodes in our distribution network. We have interactive buildings, big commercial buildings. They normally say the DNO that this much of power I need. So, this kind of interactive buildings we have. You have so many power electronic devices and layered and hierarchical control schemes. So, if you do not manage your grid edge resources properly, then you will create more nuisance and can be a huge source of new types and grid services are coming up in the next few years. So, if you do not give a proper management, if you are lacking of management of these resources, then your facilities will remain underutilized, and that is why you need a distribution and grid edge optimization or control algorithm. So, these are the services normally we follow for distribution grid. That grid service are requested normally in the modern power grid. They request the customer for getting some benefit, and then customer reply them back if they can do it or not, or if they can do in certain how limit they can do. So, these are the few specific distribution network grid edge services: frequency response, voltage management, black start, regulation, reserve and energy schedule. And that is done to do the grid operational objectives, like from the DNO perspective, it will be done by peak load shaving, voltage support, frequency regulation, load shaping, spinning reserve or emergency power that you will get from this. Again, if you are a provider or a generating power plant, then you need a backup power for the black start capability, you need increased PV or self consumption for the energy schedule properly, you need demand charge mitigation, you need time shift charging TOU optimization and energy arbitrage. TOU optimization means it is a time of use optimization that you will do for the energy schedule. So, this kind of a grid services you have or you have to ascertain in your network. So, we will see why you need an OPF in a distribution grid, why you need a smart optimization technique. So, let us say this is a synthetic distribution system of San Francisco Bay Area. Just for this small area region, we have sub-transmission network, 3-phase medium voltage, single phase, 3-phase low voltage and single phase low voltage. So, this small area has almost 22,65,000 of building customers, and total number of customers is 42,99,805. So, number of electrical nodes you can see it is 98 lakhs, that means almost 1 crore nodes you have. Then you have substations, you have lines, sub-transmission lines, medium lines, everything. Now, you imagine the size of this complexity of this network. You have to solve the OPF problem for this big network. This is just a simple city you can say of US. So, you have to solve the OPF problem for it. So, you can imagine how hard to model this problem and how difficult to solve this problem. So, if you go with the traditional rule based control, that means if this much of load is there, we will turn on this generator. If this much of load is there, we will turn off the capacitor bank. If you go with this kind of rule based problem, then we will go nowhere with this much volume of a system. If it's the volume of a system is that much big. So, rule based system will not work, and you need a efficient algorithm to get the low cost, reliable and resilient power supply. So, that is why your DOPF is different from your TOPF. And why it is different? First, the thing is that you have a 3-phase unbalanced loading, you have mutual coupling among the different phases, which is not present in case of transmission grid. You have single phase and 2-phase branches. It is a radial topology with high R by X ratio, whether your transmission grid is meshed and low R by X ratio. You have large penetration of DERs in the network. You have voltage dependent loads that we have already studied, that is the ZIP load. You have needs highly efficient algorithm. So, with few assumptions to omit the non-convex expressions. So, DC OPF further DC OPF is not possible, which is very easier to implement for transmission grid, but that is not possible for distribution grid, as you cannot neglect the network loss in distribution network, because you have a very high value of R. Okay. So, this is your distribution network OPF structure. Your objective function will be minimization of energy cost, minimization of energy purchase at the main substation. You can take total power loss or maximize PV hosting capacity, voltage deviation and DNO profit. This kind of maximize of DNO profit you can take as an objective function. Your constraints are power flow constraint, node voltage limit, line thermal limit, DER operating limits and others. Your decision variables will be how much power you are taking from the main substation, active and reactive power set point for your all your DERs, tap position for your voltage regulator and switching status of the capacitor bank. The parameters you will take, that is the load demand, your energy price for the upper grid, that how much price you are buying or you are offering to your customers, DER generation and the parameters and the customer details you have. So, considering this, we will formulate the distribution OPF problem in the next class. So, I will end here and we will meet in the next class. Thank you.